Lucas numbers. So Lucas numbers or Lucas sequence is 2, 1, and L0 is 2, L1 is 1, and then to find Ln, we add Ln minus 2 and Ln minus 1. So in other words, if I want to find L3, I go 3 minus 2 plus 3 minus 1. So L3 is equal to L1 plus L2, or L3 is equal to, I'm sorry, I went too fast. I need to find L3, I need L2, and I don't have L2, so I need to find L2 first. So to find L2, because that comes next, I have L0, I have L1. To find L3, I need L2, and L2 is equal to, again, 2 minus 2 plus 2 minus 1. So L2 is equal to L0 plus L1. And L2 is equal to L0, which is 2. L1 is 1. So L2 is equal to 3. And now I can find L3 because L3 is L1 plus L2. So L3 is equal to L1, which is 1, and L2, which is 3. So L3 is equal to 4. So the sequence goes like 2, 1, 3, 4, or I can just use what I have in front of me, add the two previous one, 3 plus 4, to get the next one, which is 7. 4 plus 7, it gives me 11. 7 and 11 gives me 18, dot, dot, dot. But as you see, if I want to find A or L20, I need to know L18 and L19. So I have to find L18, L19, and then to find L18, I need L16 and 17 and so forth. For that reason, we can come up with an explicit formula to find a particular Lucas number. So let's say if I want to find this one without knowing the two previous one, we can use a formula which is called an explicit formula. But before we find the explicit formula, we have to talk about the generating function. So Lx is equal to 2 minus x, 1 minus x to the power 2 is called the generating function for Lucas numbers. Now we want to prove that this is the generating function. To prove that this is a generating function, we have to use power series. So we let L of x equals to a instead of an. That is the notation most textbooks use. I'm going to use ln xn. We call this a power series. We have the recursive formula which says L0 is equal to 2, L1 is equal to 1, Ln is equal to Ln minus 2 plus Ln minus 1. So we are going to use these two for the proof, to prove that indeed this is the generating function for the Lucas numbers. And after that, I show you what the generating function is going to do for us. So first, I'm going to expand L of x. I'm going to write it as, and it starts here from 0. So I'm going to write the 0 term. So I get n is 0. So I get 0 and x to the power 0. Plus when n is equal to 1, I get the next term, which is L1, x to the power 1, plus I'm not going to write the rest of them for n is equal to 2. And leave it like that. Then I'm also going to replace ln, this ln, with that. So let me do that. I'm going to replace the ln with ln minus 2 plus ln minus 1 xn. So remember, this is ln. And then I use the sigma property. I can break this into 2 terms. And I also will substitute for L0. L0 is equal to 2. L1 is equal to 1. So I will write L of x is equal to 2. X to the power 0 is 1. So I get 2 times 1 is 2. Then I will put plus. L1 is equal to 1. X to the power 1 is 1. So this is 1x. So I just write it as x. Then I put a sigma notation for this one, ln minus 2 xn, plus a sigma notation for the next term, ln minus 1 xn, and goes from 2. Because eventually I want to do some algebra here, I need to change this n is equal to 2 to n is equal to 0 because I want to substitute this eventually. So for this substitution, I need to have a 0 here. So if I change this to n is equal to 0, I have to adjust these subscripts. So if n is equal to 0, I have to change n minus 2 to n, but then I have to change this to n plus 2. And if I don't, I just want to show you the justification for that. So suppose I had n is equal to 2. Suppose for that n is equal to 2. If I put 2 here, I get 2 minus 2 is 0. So I get L0. If I put 2 here, I get x to the power 2. And then if I change it to 3, I get 3 minus 1 here. I get L to the power, L of 1. And then if I put a 3 here, I get x3. Now look what happens with the new changes. With the new n equal to 0. I put 0 here, I get L0. I put 0 here, 0 plus 2 is x to the power 2. And if I change that to 1, I put 1 here, I get L1. And if I put 1 here, I get 1 plus 2 is 3 plus dot, dot, dot. So you see nothing changed when I change n is equal to 2 to n is 0 and adjust these. I do the same thing here. Before I expand, if I put 2 here, I get L, 2 minus 1 is 1, and x to the power 2. If I change that to 3 to write the next term, 3 take away 1 is 2, x to the power 3 plus dot, dot, dot. So let me change that to n is equal to 1. If I change it to L, n is equal to 1, this is going to change to n. And then this will change to n plus 1. So when I put 1 here, I get L1. And this is just going to be 1 plus 1. I get x2 plus, when I change n to 2, this is going to be L2. And this is going to be 2 plus 1 is 3. Plus dot, dot. So far is good. But I also need to change it one more time. This time I want to change that to n is equal to 0. So if I change that to n is equal to 0, there's nothing else I can do about these n's. I'm just going to write what I end up with. When I change n to 0, I get L0. When I put 0 here, I get 0 plus 1. X to the power 0 plus 1 is x to the power 1. Plus, then I change n to 1. And when I change n to 1, I get L to the L1, and x to the power 1 plus 1 is 2, plus L2, x to the power 3. So as you see, these terms are okay. I just have this additional term, and L0 is 2x. So what happened is, for n is equal to 0, ln x to the power n plus 1 is going to give me 2x plus the rest, plus n is equal to 1, ln xn plus 1. So to justify for this term, what I will do is I just write this as Lx is equal to 2 plus x. This one is already okay. Its n is 0. I have ln x to the power n plus 2. The next term is going to be 1 plus. Since I have that 2x, I'm just going to write it as 2x instead of this. I'm going to subtract the 2x and then write that, because this is equal to that. So I just want to get rid of that 2x, so I subtract the 2x, and then I write this notation. N is 0, ln x n plus 1. Next, I'm going to write this x to the power n plus 1 as x to the power n times x, and this x doesn't have an n, so it can come outside. The same thing here. I can write that x to the power n times x to the power 2. This x to the power 2 could come outside. So I get 2 plus x to the power 2 ln x to the power n, and it starts from 0. I have a minus 2x plus, instead of that, I'm going to keep the x outside, and it starts from 0, ln x, xn. So next, what I'll do is I'm just going to change that and that to this guy, L of x. So that's equal to L of x. So I can write L of x is equal to 2 plus, I can add x and minus 2x. Those are like terms. So I get this and this are like terms. So I get 2 minus 1x minus 2x is minus x, plus x squared L of x plus x L of x. Now I'm going to move the L, the rest of it is just algebra. I'm just going to move this to the other side. So what I end up with is L of x. I'm going to write this one first, minus x L of x, minus x to the power 2 L of x, equals to 2 minus x. I factor L of x to get 1 minus x to the power 2 equals to 2 minus x. We divide both sides by 1 minus x squared. So we can write L of x is equal to 2 minus x, 1 minus x to the power 2. So I use the power series, I use the recursion formula, I came up with this function. And what is interesting about this function, I can use partial fractions and write this as two fractions that are going to be written as converging geometric series. So to do the partial fraction, I'm not going to show you all the little details. I just want to show you how you can factor this one. To write this as a partial fraction, obviously you write this as a over a factor plus b over another factor. But to find the factors, you have to factor this one. If I factor a -1 from here, I get x to the power 2 plus x minus 1. I'm trying to find these factors to write this as a partial fractions, to write it as two fractions. So I use the quadratic formula to find the two factors. It's -1 plus minus b squared. B squared is 1 minus 4 times a is 1, times -1, that is our c here, divided by 2. So I get -1 plus minus, negative times negative is positive, 1 and 4 is 5, divided by 2. So the factors are going to be, I'm just going to manipulate that. If I multiply this by a negative, I will, if I multiply this by negative, or I'm just not going to multiply that by negative yet. I just want to show you that I can write these minus x1 as, if I multiply this with a negative to find one of the factors, I get negative times negative is +1. Negative times that negative is going to give me positive square root of 5 over 2, which we call it phi, which is the golden ratio. And minus x2 can be written as, again, I multiply it by -1. Negative times negative is positive. Negative times that positive is negative. A square root of 5 divided by 2, which is, this is xi, which is 1 minus phi. That's what that is anyway. So therefore, I can write the factors as 1 plus phi, 1 minus plus xi. And when you do the partial fraction, eventually you can write L of x, which is equal to 2 minus x, 1 minus x minus x to the power 2 when you solve for a. What you will get is the following. You will get 1 over 1 minus phi of x plus 1 over 1 minus xi of x. So you are able to write, and then again, this is phi, this is xi. So you are able to write it like that because you will solve and you get a and b is equal to 1. And then you can manipulate that and write it like this. I'm sorry, I had to put an x here, right? X times that. I'm trying to factor this. When I factor it, I get x, and then I can put plus phi and plus xi. So I forgot to put an x here. So anyways, these are what you get. And then this is a geometric series that will converge to phi of x to the power n. And this one will converge to xi of x to the power n if phi of x is less than 1, if xi of x is less than 1. So this is going to be written as a geometric series if phi of x is less than 1, absolute value of phi of x. And this is another geometric series that can be written as a power series if xi of x is, absolute value of xi of x is less than 1. So now from here, we can write this as phi to the power n, x to the power n. And we can write this one as xi to the power n, x to the power n. And then we can put these two together, and then phi is equal to, if you remember, 1 over, I'm sorry, not 1 over, phi is equal to 1 plus the square root of 5 over 2 to the power n. And I can write this one, join these two series as 1. And this is 1 minus the square root of 5 over 2 to the power n. And then x to the power n. So now this piece is the explicit formula for L sub n. So L sub n is equal to 1 plus the square root of 5 over 2 to the power n plus 1 minus the square root of 5 over 2 to the power n. And also, when you put this in a calculator, you get negative 0.6 something. And when it's raised to the power n, let's say when I raise it to the power 2, this gets a smaller. When I raise it to the power 3, it gets a smaller. So to find the explicit formula for L sub n, you could almost ignore this one and round whatever ln is, and that will be the nth term of the Lucas number. So we are going to look at an example. So let's say we want to find L6. So if I put 6 here and 6 here, so we get 1 plus the square root of 5 to the power 6, 1 minus the square root of 5 over 2 to the power 6. As I said, when you raise this to the power 6, this number, since it's less than 1, is going to get super small. Is going to be 17.944 plus 0.055. And when you add them, you get 18. Or you could round whatever you get for L6 just using the first term. This is 17.944. And if you round it, you get 18. So you can just use this term to find the Lucas nth term of the Lucas sequence. So it's the sixth term is 18. This is the 0, 1, L2, L3, L4, L5, L6 is 18. And that is the end of the lesson.